Hello, my name is Eric Lee, and this is image morphing with Delaunay Triangulation. So our main goal for this project is to essentially interpolate between two images. So on the right side we have our naive crossfade animation. So this is just taking the color values of the two images and then just taking a slider and then just dragging that percentage color of that image onto our final product. This is clearly not the best way we want to morph between two images. If we want to morph between two images, we would ideally want to map similar features onto each other. For example, we want the eyes to map to one another, the mouths to map to another, and more importantly, we want the general head shape to map to one another. And that starts with triangulation. So the main idea of our project is that we're going to take two different images and make two separate meshes of these triangles or simplexes. And we're going to take these triangles and we're going to linearly map each of the simplexes from one to another. Now, if we go ahead and talk about how do we actually triangulate this, so we're using a method called Delaunay Triangulation. And the core idea of this is that it essentially takes the plane and creates a convex hull around it, and then subdivides that convex hull into a bunch of triangles. Delaunay triangulation is formally defined by a triangulation of where the circumcircles do not contain any of each other's vertices. The sort of main reason that we're doing this is because it's a good way to avoid these really sharp triangles or really thin triangles, which we call sliver simplexes. Delaunay triangulation also happens to essentially maximize the size of the smallest angle in any of the triangles, which avoids that main problem. It's also interesting to know that Delaunay triangulation is actually a dual problem to the Voronoi diagram, which essentially takes a bunch of points and then takes the minimum distance away from those points to sort of divide a huge plane into subplanes. This is also just a convex hull optimization problem, so we'll just be using a existing library called QHull that solves these types of problems. So our solution is to essentially take the two meshes that we have between them. So the meshes are purely defined by the points, taking the average of those points and calculating the Delaunay triangulation of that. And the result of that, if we map back those exact same points to their respective triangulations, is that they create this sort of pulling effect. Because the triangulation were made from the midpoint of these, it understands where the main groups of items are. The most notable example here is the hair. So the hair in the left figure has much longer hair, so it's pulled down. And the hair in the right figure is much more shorter hair, so it's pulled up. And we can physically treat these sort of as like rubber bands. This rubber band of triangles is pulling the hair up. This rubber band of triangles is pulling the hair down, so that when it interpolates between the two of them, it understands that it needs to map from the lower ones to the upper ones. So let's get to actually talking about image morphing. So now that we have the triangulation of both images, we want to map the triangles from one to another. The basic idea of this is that we're basically just going to take the points inside of one triangle and then linearly map them to the other triangle. You might be able to note that this is an affine linear transformation between two 2D shapes. So this actually requires a three-dimensional matrix. The main idea for this is basically we're going to take each of the coordinates of the triangle and we're going to add a fake z-axis. So that makes all of them linearly independent. So the right side here is just going to take the first triangle and then go to the space where the basis is here, and then sort of do a change of basis. So we're going to change the basis from one triangle to the other triangle, adding this fake one extra dimension so that the matrices are invertible. And this is our very simple linear mapping between two triangles. We can see that we have exactly what I described, with the hair that's down here being pulled upwards to match Jamie Moscato's hair. But there is a problem with this simplex mapping, which is that simplex mapping is over a continuous space, but our images are discrete pixels. So how do we go about sampling different types of colors? So we're going to be using inverse color sampling. And the idea is that we have two different ways to select colors. We can take a grid of pixels from our original image and then transform them forward as our animation occurs. This has a bunch of problems. The main problem is that when the pixels transform forward, we don't know how wide that transformation is going to be. We might start with a very small triangle and end up with a very large triangle, and that means there is a huge gap between the pixels that we have to interpolate. We want to go the opposite direction. So the idea is that once we do this transformation, we can then figure out, okay, I'm at this pixel, which pixel do I have to select from the original image that will match the color best. And now it doesn't matter if the transformation is sparse or not. Once we do sample the color pixel backwards, we're going to use bilinear interpolation to just choose the color if it lands between two different pixels. So this is a visualization of where the colors are going to be sampled. So this is from alpha equals 0.4, which basically means about 40% way through our transformation. And we can see here, this is where the sparsity comes in. The transformation between the two hairs stretches out that area a lot. If we were to do this forward sampling instead, transforming from Jamie Moscato to our mid-frame, then we would have our mid-frame have a bunch of these 5 pixel wide gaps, which is going to be very problematic. So here is an example of our final product, our transformation between Idina Menzel and Jamie Moscato. So we see that the hair is being pulled up. Maybe our mesh wasn't designed optimally, so the ears are considered to be sort of part of the hair for now. And this is another example. So we have Brady Balla, who's another student taking this class, as well as actor Jesse Eisenberg. And we have 2 meshes created for both of these people, and the meshes are transforming with one another. So here we have a few more examples. So these are 5 cats that I took from r/blep. So a mesh was created around their face, their eyes, as well as their tongue. And we can see that it's being interpolated between these 5 cats very seamlessly. We have one image here, as we can see, that has a very different rotation from the other ones, but still handles those transitions very well. Since our mesh only focused on the face, eyes, and mouth, it looks nothing else. The background might be a little wonky, but the faces are transitioning very well, I think. So let's talk about actually morphing just the meshes themselves. We have prospects like animation. So this is taking the flowers, adding a very simple mesh around the flower, and then just twisting that around. So our first example is rotation. We made a very big mesh around this petal, and then we just took that mesh and rotated it a little bit. And we can see the result is a full animation of that petal transforming. Another application of this is to create caricatures. So we have the face of Jesse Eisenberg and then a caricature image that I found on the internet of Jesse Eisenberg. I took the 2 meshes and I transformed Jesse Eisenberg's face into the caricature in real life, which sort of creates this terrifying effect, but it does sort of show off the possibilities with this tool. And now we'll go to a live demonstration of our tool. Alright, so this is going to be our demo. So here we just have a folder with 2 images, an empty folder called frames, and our script morph.py. Our 2 images are going to be blep1 and blep2, both images that we've seen before. If we run morph.py-h, we can see the parameters that it sort of wants to take. So it takes in the 2 images that we want to interpolate between, as well as the meshes for those 2 images. We can specify how many frames it generates, as well as how the file is going to be stored afterwards. The main thing here is the task, though. Interpolate images, which is the default setting, just does what you expect, take those 2 images and meshes, and transforms between them. Interpolate mesh basically throws away the secondary image and just only sample from the first image. So this is going to be more of our flower transformation or a caricature formation. The third option, draw mesh, is a quick utility that we can use to select points to essentially create our meshes much quicker. So we can call this function supplying it with our image and telling it that we want to create a CSV file that stores the meshes. So we'll tell it to use the task of draw mesh. And let's just go ahead and click our points. Alright, so we have our simple mesh around the face, eyes, and mouth. And we'll now do the same thing with the second image. Alright, and we have the same type of mesh for this demonstration. So now if we go ahead and open both CSV files, you can see that they just store the x and y coordinates of both. So now if we go ahead and run our morph with our standard blep1.png, blep2.png, and now supplying it the meshes, which is the 2 CSV files, we can tell it to output a file name called blep and tell it to generate 20 frames. Alright, so it looks like our code took 4 minutes and 53 seconds to run, just on a single thread. That's about 15 seconds a frame. So now if I go ahead and just do tree, we can see that it generates all of the frames and saves them in this frames folder, but it also collects them all into a single GIF where we can see our final product. All of the code, images, and GIFs that are generated are stored in this GitHub repository if you want to look into that. If you have any questions, now would be the time to ask. Thank you.